Good evening, everybody. Welcome to our third model speaker. I'm Herman from SPA Northern Iraq section. I want to welcome Professor Dr. Azeez Barzinji, and he will present the Green Nanotechnology, Sustainable Sciences, and Practical Application. I want to introduce Dr. Azeez profile, and he has completed his bachelor degree in physics in 1998 in University of Salahuddin, Erbil, and has completed two master degree in superconducting transmission line and master in theoretical physics in 2004 and 2009. Also, he completed a doctoral degree in the material science in 2014 in the University of Leicester in United Kingdom. Also, he published over 130 high-impact scientific articles and received more than 2,600 citations, which an high index of 28. Also, current research interests include green synthesis of nanoparticle metal electroplating from novel ionic liquids and properties investigation, solar selective coating and surface plasma resonance, and nanotechnology. And his current position is full professor at Soran University, and supervises several master and doctoral students at Virus University, and recognizes. And I wanna share that Dr. Azeez has been listed among the top 2% of the world scientists, which which selected by Stanford University. Now, Dr. Azeez, the mic is yours, and you can start.
Okay, I will share my screen first if you want.
Yes.
So can you see my slide, right?
Yes, Doctor.
Okay, Bismillah ar-Rahman ar-Rahim. First of all, I'd like to thank SPE in Kurdistan, Northern Iraq section, for inviting me for this wonderful event. I hope during this limited time I can explain the green synthesis nanoparticle and the application, and highlighting some recent application from our side. Okay, so in this talk, I will introduce general idea about nanoscience and nanotechnology, and also I will explain how things behave in a small scale, and also I will explain nanoparticle synthesis and green synthesis method, mechanism for formation nanoparticle, application, and also highlighting some recent finding. First and foremost, nanotechnology and nanoscience became like the story of the blind and the elephant. Everybody define nanoscience and nanotechnology from their perspective, and unfortunately, none of them are right. We should take the total image, the entire image of nanotechnology in order to understand. So the blind, when they want to define or describe elephant, some of them said it's a rope, wall, fan, spear, snake, and tree, but none of them were right. So the nanotechnology in this time, in this specific time, became like this. So everybody want to work in nanoscience and nanotechnology unfortunately, without having general idea, general picture of nanotechnology. So in this presentation, I will try my best to explain the total or entire image for nanoscience. Since I have a art background, so for me, nanoscience and nano art are similar. So I will start my presentation with the famous statement by Michelangelo, who said, "Every block of stone has a statue inside it, and it's the task of the sculptor to discover." So in order to produce a statue, you either start with a big stone in order to produce a statue. This is exactly a top-down approach in nanotechnology. Or you can bring the sand and then mix it with water in order to produce a statue, and this is called bottom-up approach in nanotechnology. So we have two approaches to producing nanoparticle. But the real story starts from the famous talk by Richard Feynman, which was the Nobel Prize winner in 1965, the American physicist, who gave a very special presentation in late December 1959. The title of his speech at that time was, "There is plenty of room at the bottom." And during his speech, Feynman introduced very strange statements such as, "Why cannot we write the entire 24 volume of the Encyclopedia Britannica on the head of a pin?" So this is literally mean that why we can write all of this volume on the head of the pin. And the pupil, I'm sure you as well, they all surprised how we can do that. And at the end of his talk, he said, I will announce two challenges from my pocket, $1,000 for each. One of them for micro writing and the other one for micromotor challenge. And 1 year later in 1960, Tom Newman could write the dignitel on a very small piece of plastic, 200 micrometer by 200 micrometer. This is the entire dignitel, okay? And then he won the prize of Feynman. At the same time, McLellan produced the first micromotor. And this is the micromotor, and Macmillan with Feynman looking at the micromotor under the microscope. You can see that the micromotor were working, and it's smaller than the head of the pin. Okay? And nowadays, we are lucky because we have a crystal Quran, which was produced in 2001 in Belgium. And this is the entire Quran only in a piece of plastic again, 0.9 centimeter by 1.5 centimeter. And if you put this Quran under the scanning electron microscope, then you can read the entire Quran with all of the details. At the same time, we have a nano Bible, which was produced in 2015 from the Haifa Institute. This is the Bible, the smallest Bible in the world, and this is contain 1.2 million letters. In order to read it, you have to put this nano Bible under the scanning electron microscope, and this 1.2 million letters written in Hebrew. And also we have a scan disk, 8 terabyte disk, which is sufficient with 100,000 hours audio and 2 million photos, 550 or we can say 550 million books, and 10,000 hour video. This is only in 3.9 by 3.9 inches, and the thickness of this disk is only 1.5 inch. So we can put all of these things in this small thing. So Feynman was right when he said there is plenty of room at the bottom. Now, in order to make it clear, now the population of the globe is about 8.2 billion. And then the total area, land plus water, is about 510 million kilometers square. And if you divide the population by the area, then we have 16 people per kilometer square. But in fact, 1 kilometer square is sufficient for 10 million people. you can put entire American people in only 5.8 by 5.8 kilometer, and you can put all of the human being in only a piece of land 28 kilometer by 28 kilometer, which is very close to the New York City area. So this is entire human being. We can all stand in New York together, shoulder by shoulder, and without any problem. And this is Iraq. So we are in Iraq, we are about 46 million, and this is Erbil. And then this is me living in 5 people living in 200 meter square. So Feynman was right when he said there is plenty of room at the bottom. This is the computer during Feynman time. The human being can walk around it, inside it. And this is the faster and smaller computer in 2024. And this is the TV in 1959. And this is our QLED, quantum light emitting diode TVs. And this is the first transistor which was produced from the Bell Lab in 1947. And nowadays we are very lucky because we have single atom transistor in 2024. The word nanotechnology introduced formally in 1974 by Professor Norio. Norio was a Japanese professor, and he published an article entitled On the Basic Concept of Nanotechnology. So Norio was the first person who produced nanotechnology. Feynman didn't mention nano and nanotechnology at all. So he always talking about nano without mentioning nano, okay? But formally, the nanotechnology introduced in 1974. So what's nanotechnology? Nanotechnology is the manipulation and manufacture of the material and device on the scale of atom or smaller or group of the atom. Okay, so we have the nano element. So nanoparticle is about 10 to the power minus 9 meter. When you change the size of the particle, scientists can put the desired property of the material. You can play around with the material. You can enhance all of the properties of the material, including physical, chemical, and then mechanical properties of the nanomaterial. But the nanoscale, as I mentioned, is between 1 to 100 nanometer, and this includes nanotube, nanoparticle, quantum dot, and nanoshell. But of course, we have smaller than nanoparticle and bigger than nanoparticle. These are some example of the, for example, water molecule is 0.1 nanometer. And on the other hand, we have a virus, which are about micrometer, and bacteria and red blood cell as well. Here in this talk, I will talk about nanoparticle only because we don't have time to mention all of this nanomaterial together. So the first nanoparticle introduced in 1996. So this is buckyball. This is the natural nanoparticle, which is it has the diameter of 1 nanometer only. And this scientists, they won Nobel Prize only for discovering the buckyball. 60 carbon together make a buckyball. The diameter of the buckyball is 1 nanometer only. And in order to understand how small is buckyball, so it's like the size of the globe is 100 million times bigger than that's the size of the football, and the size of football is 100 million times bigger than the size of buckyball. And this is how small the size of buckyball. So in order to see the nanoparticle, there is no way to use the normal microscope, because in normal microscope you are utilizing a visible light, and the wavelengths of the visible light between 400 to 650 nanometer. So there is no way to see the nanoparticle within the normal microscope. So in this case, we should either use transmission electron microscope or scanning electron microscope. Otherwise, there is no way to see the nanoparticle. Not only this, but also particle in nanoscale interact differently with light. So here we have a bulk gold, which is the size of each particle is about 5 millimeter. On the other hand, I have nano-sized gold, which is only 5 nanometer. So you can see that the gold is not the shiny color anymore. So it will change the color according to the size of the particle that we have. So this is gold inside water. So it's not like a bulk material. For example, 10 nanometers show me red color, while 100 nanometer is like white color, or 80 nanometer is a green color, and so on. So the interaction with light with the gold nanoparticle depend on the size of the gold nanoparticle. So in order to understand nanoparticle, there are two main properties of the nanoparticle. The first one is surface area per unit volume. The second one called quantum confinement. I'll try to make it as easy as possible. So let's start with surface area per unit volume. When you go to the nanoscale, we have huge surface area per unit volume. For example, if I have a nanocube, so this is 1 nanometer each side, and then the surface area in this case will be 6 times 10 to the power 9 per meter. And if I change the shape from the cube to the sphere, then I have 3 times 10 to the power 9 per meter. So you can see this is the huge surface area per unit volume for this small nanoparticle. While if I have a cubic sugar, this is the normal cubic sugar that we are using for our daily life. So this is 1 centimeter side each. So this has the surface area per unit volume only 600 per meter. And if you have a powder sugar on the other hand, then you have again 3 times 10 to the power 9 per meter. So this will give you the QY, the powder sugar dissolve faster than the cubic sugar. So when you break up the larger mass into many small masses, you increase the surface area that is in contact with the solvent. Now, in order to give you a general idea, if I have 1 gram of nanoparticle, for example, in this case, I have copper nanoparticle, and this 1 gram of nanoparticle is sufficient to cover 2 tennis court area, each of them 260 meters square. So I can cover 2 tennis court area by having every single point in this court area contain a nanoparticle at least. So this is the beauty of nanoscience. So it has a very high surface area per unit volume. Not only this, but also most of the atom at the nanoscale will be on the surface. So it's not like a bulk material. When you go to the bulk size, then you have a specific amount of the atom on the surface. But when you go to the nano size, on the other hand, you can see that the yellow color here representing the surface atom and the blue color representing the inner atom. So you have a huge number of the surface atom when you go to the smaller size. And this will give you another chance to interact with the surrounding. So here I made a calculation for palladium nanoparticle this time. So this is palladium. The radius of the palladium is 1 nanometer only. Then I calculated how many atoms of palladium I have in this 1 nanometer nanoparticle. So it was 285 atoms. And then I calculated also the surface atom. So it was 177 atom, which is precisely about 62% of the atom. So 60% of the atom will be on the surface, and only 38% will be inside the atom. So this is the beauty of the nano size. And here I made a comparison between different shape of nanoparticle. For example, disc, ellipse, sphere, cylinder, cube, and star nanoparticle, in order to tell you that how many atoms I have in 1 nanometer size. So you can see that the highest number go to the star nanoparticle. But if I want to find the surface nanoparticle, then in this case, the cubic nanoparticle and the spherical nanoparticle, they have the highest rate of the atom. And this is again the total atom compared with the surface atom for different shape of nanoparticle. Also, when in our normal life, when things get smaller, they become weaker. But this is not the case in nano size. So ants can lift, for example, up to 10 times their own weight, while the average human can lift truly their own body weight. So it's exactly the case of nanoparticle. It's smaller, but it's stronger at the same time. Okay, let's explain the quantum confinement now. So this is the normal wire. When you have electric circuit, the electron in this case act as the particle. You can see that. So you have a single atom moving, and then this create a current, and then you can turn on the bulb. You can see the light. But if you put the electron inside the box, but here we are focusing on the nano box, then the electron behave as a wave. So this is called quantum confinement. Why this happened? So when you have a more degree of freedom for the electron inside the box, then you have less energy. In this case, we have high wavelengths. So the biggest cube, you have more degree of freedom. That's why the color of the particle will become red. And then if you go to the other side, when you have smaller size of the box, you have electron move faster, and then the wavelengths became shorter. In this case, we have blue line color. And this is explained by De Broglie, who explained that the quantum confinement appear only when the size of the particle is comparable with the De Broglie wavelength. So in this case, I calculated the wavelengths for the electron, and it was about 0.772 nanometer, which is very close to 1 nanometer. So in this case, the size of the nanoparticle comparable with the De Broglie wavelengths, then quantum confinement will dominate. Okay, so this is the case for the nanoparticle. And if you ask me why this is important, then I will tell you that the Nobel Prize of 2022 was about the quantum lead. So this is quantum light emitting diode. So this produces a huge amount of the color, because every single point on the screen can create a color, and in this case the color will be enhanced. This is much better than the normal LED TVs. Okay, so in order to understand nano, you have to focus on the quantum mechanics. So we cannot use classical mechanic and relativistic mechanic. We should go to the quantum mechanic, because as you can see that the size when gets smaller, then you cannot use the classical physics anymore. Now, the question is how many methods we have for producing nanoparticle. So we have three main methods: physical, chemical, and biological method. But of course, there are some drawbacks corresponding to the chemical and physical method, such as high temperature, high pressure, expensive, and time consuming. And also we have unstable nanoparticle, utilizing toxic material, and the process is expensive and not safe at the same time. But biological method, we can use low temperature, and it's entirely green, and one pot, which means that we can produce the nanoparticle inside one beaker, and the most important is inexpensive, very cheap. So that's why we are focusing on the green synthesis method. And in the green synthesis method, we have different areas that we can select and we can work on it, such as fruits, leaves, flower, roots, fungi, algae, and so on. So these are all green. We can use them without any toxicity problem. Okay. And also there are many factors affecting the nanoparticle preparation, such as calcination temperature, pH value, reaction time, reaction temperature, precursor concentration, extract concentration, and plant species. So you can play around with these parameters in order to produce different size, different shape of nanoparticle. So all of these parameters are affecting the shape and size and also the properties of the nanoparticle. Why we are using plant extract? Because plant extract contain phytochemical, and these phytochemical are important for reducing, capping, and stabilizing of the nanoparticle. And these steps are very important in order to produce nanoparticle. You can see you have a variety range of the fruit and plant, you can use them and as a reducing, capping, and stabilizing agent. Here we have an example about how we can produce, for example, silver nanoparticle. So first you need to prepare silver solution, which is just by adding silver salt with deionized water. Then you should add the extract dropwise to the silver nitrate solution until you have the color change, and then the color change is the first indicator for producing nanoparticle. So you can see at the beginning, the silver nitrate solution was colorless. Then when we add the plant extract, the color of the mixture became browny and reddish after 30 minutes, and then the nanoparticle is formed. Then you can synthesize your nanoparticle by using different characterization techniques such as SCM, EDX, and XRD, and so on. And this is the mechanism of formation nanoparticle. So here we are focusing on the time. So you can see that at the time starting from 10 minutes, 20 minutes, 30 minutes. So you can see that the optimum time here in this case is 1 hour. So 60 minutes, you can get the optimum nanoparticle. This is according to the Drude-Lorentz model for surface plasma resonance. And this is another case for oxide nanoparticle. So here we use the extract of the plant, and then we produce the nanoparticle. But one thing is very important, which is before using the extract of the plant, you have to test the plant extract to see whether it contains a suitable phytochemical or not. In this case, we have two different phytochemical. The first one appeared at 278 nanometer, and the second one appeared at 325 nanometer, and each of them belong to one of the phytochemical. And you can see each phytochemical contain many OH groups and CH group, which are important for producing nanoparticle. But the same graph we have, the second graph we have for the nanoparticle preparation and also finding the band gap. So band gap is very important in the case of the oxide nanoparticle. And also we have this phenomena that the band gap increase when you go to the smaller size, and this is also due to the quantum confinement. So you can see that the conduction, the distance between the conduction band and valence band in the bulk material is smaller than the nanoparticle. And not only this, but also the band gap became discrete. So you can see that from the bulk material is continuous, while in the nanoparticle material became discrete, and this is depending on the size of the nanoparticle. For the bulk material is fixed, but for nanoparticle, the band gap depends on the size of the nanoparticle. Here we are showing some factors affecting the nanoparticle preparation. So in this case, we changed the pH and temperature and also the concentration of the utilized salt. So you can see that every single condition gives you a specific size, specific shape of the nanoparticle. Regarding the mechanism of nanoparticle, so there are many scenarios of producing nanoparticle. This one is the best one for the metallic nanoparticle. So these are the phytochemical available inside the plant extract, and then when you add the water, deionized water with the salt, you will have the silver ion in this case, and then this plant extract, the phytochemical participating in the reducing, capping, and stabilizing of the nanoparticle. At the end, you will have a stabilized nanoparticle. And this one is for the oxide material. This is another scenario for explaining how the zinc oxide nanoparticle can be produced within the plant extract. In this case, we use the parsley extract. So this is, again, another good scenario. And this one also for the oxide nanoparticle, different types of nanoparticle, different shape of nanoparticle, And these are the process of producing nanoparticle, starting from the reduction, growth, and stabilizing of nanoparticle. And the most important is these books from the Springer and Elsevier and other publication. They utilized our references as a good scenario for producing nanoparticle. Also, we show that the green synthesis method is always better than the chemical method. So in this case, we utilized green synthesis silicon dioxide nanoparticle and also magnetite nanoparticle using plant extract and chemical method. So here we are showing that always the green synthesis nanoparticle is better in terms of stability and the size and morphology, agglomeration, everything when you compare with the chemical method. So it's not only you are using expensive material and toxic material, but also it's important to have a stabilized nanoparticle within the green synthesis method. And in this study, we show that utilizing fresh plant extract is always better than dry plant extract. So in this case, we utilize two different medium, fresh and dry plant extract, and then we show that always the fresh extract, because it contains many phytochemical, because during the drying process some of the phytochemical will evaporate it, so this will affect on the quality and stability of the nanoparticle. So far as it has been stated by the introduction, I have more than 130 publication in international journal. So our research depends on or based on the wastewater treatment, heat generation, solar cell enhancement, nanocatalysis, enhancing building material, antibacterial, antimicrobial, and producing green nanoparticle, nanorod, anti-cancer activities, nanodentistry, and also utilizing nanoparticle in 3D printing as well. This is a new project that we started on it, and also nano in agriculture with people from the agriculture engineering college. So here's some example of our work. So in this work, we could utilize it, nanoparticle for reducing chrom-6, which is very carcinogenic, available inside the water, and also we degrade different types of dye, such as methyl orange and methylene blue in water and under environmental condition. So here you can see the time of the degradation for different types of dyes, and also reduction of the chromium 6 to the chromium 3, which is much safer than the chromium 6. And here we utilize homemade pomegranate, Halabja pomegranate, in order to produce nickel oxide nanoparticle, again for dye degradation. But in this process, we could decrease the time of the degradation from 60 minutes to only 37 seconds by using the green synthesized nanoparticle. And also we utilized different types of plant extract in order to produce zinc oxide nanoparticle from different plant extract, and also utilizing this nanoparticle for dye degradation. So all of this work depend on the nanoparticle produced from green method and utilizing this green synthesis particle for wastewater treatment, either for degradation of dye or reducing ion, heavy metal ion, and so on. So this is another one. In this case, we could coat silver nanoparticle on bentonite nanocomposite in order to make the process of the extraction easier. Again, we use this nanoparticle for a reduction of different types of dye, such as Congo, rhodamine, and methylene blue, and so on. Here we utilize two different medium for producing nanoparticle using plant extract and also eutectic basic ionic liquid for reducing different types of blue dye. And this one is the very dense literature review on the utilizing iron oxide nanoparticle for wastewater treatment. Now, the second project is very important, and this is produced by our group. This is heat generation inside water. So this is very important because here you are just adding nanoparticle inside water, and then by shining light on this nanoparticle, you can make the plasmonic effect in order to generate heat inside water without any external source of heat. And this is, has been already patented in recent patent on nanotechnology. And then later we could enhance this project by utilizing different types of nanoparticle. So first we start with silver nanoparticle, then we utilize magnetite nanoparticle, zinc oxide nanoparticle, in order to find the effect of the type of nanoparticle, the size of nanoparticle on this heat generation inside water. So you can see this is this is the best we did, about 35 minutes. The temperature changed from 25 degrees of Celsius to 34.6 degrees of Celsius. So this is very important project, and this will give you a chance in order to produce heat inside water only by adding nanoparticle. And the third project is about the enhancing solar cell efficiency. We first started with the simulation in order to see what's going on, and then we started with the experimental project, which was adding nanoparticle, different types of nanoparticle on the commercialized solar panel in order to enhance the solar power conversion efficiency. So this was a great project, and we could produce several nice articles on this project. So in this project we could increase, as I mentioned, the efficiency of the solar cell, the commercial solar cell, which is very important because in normal solar cell, always we have the problem within the efficiency. And then we could utilize different types of nanoparticle from plant extract and ionic liquid, as you can see from here, in order to do that. And then we are working also on thin film preparation, and we can utilize this film for as a sensor for different gases or UV, IR, and so on. So we are we have a very strong thin film, in this case silver nanoparticle, produced from different medium, and utilize this film in order to absorb the amount of the UV. So as you can see that UV is the highest energy from the solar spectrum. So the black line here represents the bare indium titanium oxide glass, and the red one is the Ag nanoparticle produced from dry plant extract, and the blue one, which is the best one, is Ag nanoparticle from fresh plant extract. And then this project is very important because you can see that the amount of the absorption reduced from about 90% to only 40% or even less. And also we could utilize nanoparticle in order to absorb the gamma ray. In this case, gamma ray is very problematic, is a nuclear problem. So this is gamma radiation, and then we could produce a film from PBO, lead oxide nanostructure film, and then after passing gamma ray, 70% of this gamma ray has been absorbed by our film. Regarding enhancing building material, we started from the engineering point of view in order to enhance different types of material by adding our green synthesized nanoparticle. So these are some of the projects that we used. For example, nanosilica highly affected the compressive strength of the cement-based compared to the microsilica. This is another one. So this is the lime-based plaster, are extraordinarily complicated structure comprised of multi-mortars. Regarding biological project, so we started with some medical application. For example, we utilized zinc oxide nanoparticle in order to kill some unwanted bacteria. Here in this case, we have lamb liver, and then we leave the lamb liver in a bare environment in order to grow bacteria, and then we utilize zinc oxide nanoparticle. And then after a short time, we realized that this nanoparticle can kill this bacteria more effectively than the normal addition or more normal catalyst that we used before. With people from medical application, we started during the Corona time, and we published some article regarding the coronavirus. Now, this is the most important biological project that we started, and this is the utilizing green synthesis nanoparticle for anti-cancer activity. So we hope that we can elaborate this project and make it bigger project in a future, because this is related to the cancer. And this project is very, very important. And this article has been cited dramatically by many authors. Now, as I mentioned, there are two main areas for us working on it. The first one I explained it, which was the green synthesis method from plant extract, but the second one is the utilizing ionic liquid for producing nanoparticle. And the first novel ionic liquid was introduced in 2001 by Professor Abbott from Leicester University, and this is basically 1 mole kaolin chloride with 2 mole urea. And the magic thing is that these are too solid. When you mix them together, you end up with the liquid. And you can use this liquid in order to produce different types of nanoparticle. And I was lucky because I was working with Professor Abbott during my PhD time. And you can see here, Professor Abbott has a huge, very strong pure profile. And this profile dates back to the great scientists such as Guy Lossac and Lavoisier and Christian Huygens and so on. So this is me when I produced the first chromium nanoparticle from ionic liquid. So this chromium nanoparticle can be used for as an anti-corrosion. And then we utilized this chromium solution in order to find the distance between the atoms and also the number of the atom. And we did this in the European Synchrotron Radiation Facility in Grenoble, France in 2013. Yeah, so this is the how we change the coin from the copper to the chromium. This is our data by utilizing this chromium nanoparticle. We also start to produce different types of nanoparticle or nanorod from green synthesis method. And we also utilize nanoparticle for nanofluid application. So nanofluid is utilizing nanoparticle inside water and using in different application. And we have also several article reviews about the green synthesis method in different journals. And lastly, we could produce the green synthesis nanorod, which was, I believe that we are the first group to produce green nanorod. This is totally green method for producing nanorod. And we also working in the bio-nano composite with people from German University, and we already started producing some high impact article. And we're also utilizing the nanoparticle for enhancing hydroxyapatite properties which is very important nanoparticle or nanocomposite for dentistry application. Now I started another project in order to enhance the mechanical material. This is 3D. You can see that this nanoparticle can protect this 3D material from the corrosion, and also antibacterial, antifungal, and so on. And regarding the field emission, I also started some project with the people from Jordan and Czech Republic to produce the highest field emission from oxidized copper emitter. And so far I have 3 books, Green Source in Eco Nanotechnology and Strip Transmission Line Parameters, and the last one, Introduction to Analytical Mechanics. And finally, I can say that till now we did nothing, and still we have a lot of work ahead of us. And thank you for your listening.
Thanks, Dr. Azeez, for presenting this valuable presentation about the green nanotechnology.
Thank you so much.
Thank you. Anyone has a question? Please feel free to ask the questions.
Okay. Sorry if I take more than my limited time, but it was like 3 parts, like general idea about nanoscience and nanotechnology, and also how we can produce nanoparticle, and then the last part was for the application, the utilized nanoparticle in different application.
No, actually, thank you very much, Dr. Azeez. I've got 2 questions,
Thank you.
if possible, and thank you very much for your time.
Yeah, sure. Sure.
One is the nanoparticle availability in Kurdistan. Could you share with us where nanoparticles can be created or purchased in Kurdistan? And what synthesis do we have is available, like the mechanisms and techniques? Is it only the physical way? Is it only the biological way you were talking about, or are there also the physical ways?
Yes.
And is it only the universities that have established nanotechnology labs? And if there are places to purchase nanoparticles, where can we find them? Regarding my second question is the feasibility and scalability of nano applications in engineering specifically. A common question we encounter is whether applying nanotechnology in engineering is economically viable. They always ask, are there faster or larger scale methods for synthesizing nanoparticles and applying them directly in engineering fields or on-site applications, as you know, because we need larger amounts of nano for applying them in engineering specifically.
Okay.
Yeah, that's my
thanks so much, Mr. Rahman. No, we are not the only group in the Kurdistan. I can say without any doubt that we started in a very earlier time. So it was 2015, I guess, when I came back from the UK. So we started utilizing this green synthesis method, and I still remember the first article was about green synthesis of zinc oxide nanoparticle, and we published in this article in a local journal. Nobody were using green synthesis method that time, but nowadays, because we shared our information, our knowledge with everywhere. So because we are very open, we don't have any secret in producing nanoparticle, the steps of how you can produce nanoparticle. In many workshop, in seminar conferences, we told the audience that this is how we produce nanoparticle. It's not a rocket science. It's only using the extract of the plant, and then using the salt with deionized water. And even some of my BSc project students, they could make the nanoparticle, and then they published this result in a very good journal. So it's now became the very famous, and people started from biology, chemistry, agriculture, dentistry, medicine, everywhere, engineering, utilizing this nanoparticle, synthesizing this nanoparticle in different areas of application, which is great. I always encourage people to do that because we are very lucky. I always repeating this statement. We are very lucky because we are living in nano era. So we are very lucky. After maybe 20 years, we will go to the angstrom era, which is 10 to the power minus 10. So now we are lucky because we are living in this era. So we have to do something in order to record our name for the history. Regarding your second question, so you can even some of my students, they produce nanoparticle in their house. So you need a beaker, you need a hot plate, and that's it. And then when you prepare nanoparticle, then the second step is characterizing nanoparticle. Unfortunately, we don't have many places for characterization. We have only, as I remember, we have only Soran University and Slemani University for some characterization. That's it. That's why people always sending their nanoparticle either to Iran or Turkey or Baghdad sometimes, which is not bad, but it's better to have these facilities in our country. Anyway, and then regarding the mass production of nanoparticle, well, I can say without any hesitation that this is the only concern with the green synthesis method, to be honest. So we have a little yield of nanoparticle. So if you work, for example, from 9 a.m. until 5 p.m., you can produce nanoparticle, but the amount of the nanoparticle will be only 2 grams, which is very little amount of nanoparticle. That's why people are, when they are thinking about engineering point of view, because they need lots amount of nanoparticle, so they will think about the commercial nanoparticle. And the problem is the commercial nanoparticle is expensive. This is first. And second, this is toxic, most of them toxic. And the third one, they are not stable. So when you are utilizing commercial nanoparticle, you are facing all of this problem. So they should wait. For example, we had 2 PhD students. Mashallah, they did very well. They produced each of them about 8 articles, I guess, maybe more, in Soran University. But they faced this problem for producing green synthesis nanoparticle. And then they ask some assistant to do this with them. So they work day and night in order to produce this nanoparticle in order to run their PhD project. There are many people working on the chemical synthesis of nanoparticle by using sol gel or hydrothermal process in Kurdistan as well. They started doing this. But the problem is, as I mentioned in my presentation, always the stability of the green synthesized nanoparticle is better. So that's why we are focusing on the green synthesis method. So it's not about it's cheap, but also it's about the stability of the nanoparticle. Always green synthesis method is better and more effective than the chemical and physical method. I hope I answered all of the questions.
Yes, indeed. Thank you very much.
Thank you so much.
Thanks, dear Dr. Azeez. I think we have some participants have the question. Yes,
Sure.
Mr. Muhammad Ariwan, can you open your mic? Mr. Muhammad Ariwan, are you here, bro?
Assalamu alaikum.
Yes,
Alaikum
وعليكم
salam.
السلام ورحمة الله.
Thank you very much, Dr. Aziz, for this great lecture. Thank you, Mr. Rabun and the SPE staff. Doctor, I have two questions if I do not take too much of your time.
Yes,
One
Master.
of them is, most of your research, Doctor, you have done, I noticed that you have prepared your nanomaterials in the method of bottom up. Have you worked on any projects from top down, like from bulk material to nanoparticle? Because right now I'm working on a project where I have a bulk material, which is solid. It's rock samples,
Yeah.
and I'm trying to make them, change them to nanoparticles. And my second question, Doctor, is about quantum dot. Are
Yeah.
quantum dot also nanomaterial? And
Mhm.
are they possible to synthesize or not? And if they are, what are the best methods to achieve this target?
Yeah.
Thank
Thank you, Mr. Muhammad. Regarding the bottom-up and top-down approach, it's okay. You are free to select each of them, but this depends on the facility that we have. Again, this is similar to Mr. Rabun's question. When I was in the UK, there is a chance to use the laser, for example, in order to have, for example, a silver wire. Then you can bombard the silver wire inside water, then you can produce the silver nanoparticle. This is no problem. Or you can use ball milling if you want. So in this case, for rocks, it's better to use ball milling, which is a very famous and it's not difficult, problematic. So you have some ball of metallic ball, and then you can put your material inside, and this will rotate and produce the nanoparticles. So the rotation, the time of the rotation, and the size of the ball gives you the proper size of the nanoparticle. Okay. Regarding the quantum dot, well, quantum dot, I mean, in definition, literally, quantum dot is belong to the family of the nanoparticle, because when you say nanoparticle starts from 1 nanometer to 100 nanometer, so this includes quantum dot, and quantum dot from 1 nanometer to 10 nanometer. Okay, so quantum dot is smaller size particle, but the method of producing quantum dot, within the green method. So I had a PhD student. We tried actually producing nanoparticle within the quantum dot for quantum dot, but we couldn't, because due to the limited time. And then we leave it. I said, okay, there's no way to waste our time for quantum dot. But people started working on quantum dot, and I think the Nobel Prize of 2023 in chemistry was about quantum dot. And then they mentioned that the method was not green. The method was the thermal method. Okay, so if you want, you can go to the Nobel lecture for this gentleman, and one of them was from Algeria, so Arab-based scientist. So he explained the quantum dot very well, how we can produce the quantum dot, but this is not green. Again, if you are looking for the green method, again, I don't recommend you to do this. Yeah, so it's better to use the thermal method or chemical method in order to produce the quantum dot. Quantum dot is more sufficient, more active than the nanoparticle. I mentioned that the quantum confinement became dominant more in quantum dot than the nanoparticle. So the nanoparticle, any change in the size, give you different or huge change in the physical properties of the material that we have.
Thanks, dear Dr. Aziz. Also, Mr. Hassan has the question. Mr.
Yes.
Hassan, can you open your mic?
yes. Thank you so much for the presentation, Professor.
Thank
I'm
you.
Engineer Hassan I'm a PhD researcher here in University of Campania, Luigi Vanvitelli, Italy. And currently I am working on phase change materials and these nanoparticles. I have just a question,
Yeah.
curiosity. and I'm going to ask you about the nanoparticles specifically.
Yes.
That
Yes.
is there the compatibility of these bio-based manufactured nanomaterials with the phase change materials, like the way we are getting it commercially in the markets?
Mhm.
Yeah,
Yes,
so this is
sure.
what I am asking. The one thing is about the compatibility with the phase change material. In the base change material, I'm talking about the Robitherm RT45, 50, and 55, and one
Mhm.
of the biological based phase change materials in the thermally conductive polymer materials,
Yeah.
and the compatibility with it. And the second thing, the cost and economic analysis of these bio-based materials with the already commercially available stuff. Thank you.
Thank you so much. Well, I mentioned this, I guess, regarding the properties of nanomaterial. We always focus on the chemical method when when it comes to the comparison point of view. So we produce the nanoparticle. One of the question was, is there any similar method to produce nanoparticle? Well, there are some methods. We can produce nanoparticle, similar size, maybe similar morphology, but in terms of the stability, we have always this problem. So we produce nanoparticle from the chemical method, from sol gel method, but again, this is by utilizing toxic material. Okay, so when you use toxic material, this is the number one. So it is not green, okay, anymore. And the second one, when it comes to the properties of the nanoparticle, the stability of nanoparticle, and then depend on the project that we are utilizing. So, for example, if you utilize your nanoparticle for water treatment, for example, then it's very important to utilize the green nanoparticle rather than the toxic nanoparticle. When people from engineering asking me, is it allowed to use chemical method to produce nanoparticle for adding this nanoparticle inside the cement, for example, then I will say, yes, why not? It's absolutely fine. But there is a problem when you utilize this nanoparticle for biological application or dentistry application or antimicrobial application, antifungal application. So we are utilizing this nanoparticle, adding nanoparticle inside the paint in order to use as antibacterial activity. But this nanoparticle, if they are toxic, then we are increasing the toxicity of the environment that we live. So this is the problem within the commercial nanoparticle. They don't care about these properties. They only care about the producing mass product of the nanoparticle. Believe me, I sent the commercial nanoparticle and green synthesis nanoparticle for bed analysis, if you know this test. So bed analysis will give you the surface area per unit volume. And the surface area per unit volume for our nanoparticle were much bigger than or higher than the commercial nanoparticle. And it was written on the nanoparticle, this is 50 nanometer size. But unfortunately, the shape of the nanoparticle will not give us this high surface area like the green synthesized nanoparticle. So this is the problem that we face. That's why we are not interested in this chemical or commercial nanoparticle anymore. Any other question?
Thank you.
Thank you very much.
Thank you, dear Doctor. Anyone has a question?
Look like no one has a question anymore.
Yes, dear Doctor. Thanks for your presentation and
Thanks
your
so much. Thanks so much.
knowledge shared with us. Thanks
Thanks so
for
much.
your participation, guys. Have a nice time.
Thanks so much.
Thanks, dear Doctor.
Thank you very much.
Thank you.
Thank you.